All right, aerospace engineers. This one's a little different. This is the physics of orbits, basic introduction to them. But now that you have the introduction of orbital mechanics, the hope is this one makes a bit more sense. The simplified version of this is that there's two types of energy with an orbit: potential and kinetic. And we use the energy relationships to determine how to get a satellite into a new orbit. Definition of potential energy: energy that's stored within a system because of where it is. Potential energy has the potential to get into other forms of energy. Kinetic energy is the energy of motion. Both forms of energy are important to satellite orbits. The gravitational pull of Earth gives us the potential energy. So satellite movement has kinetic energy. When we consider the gravitational potential energy of a satellite orbiting Earth, we're talking about stored energy. We're talking about the gravitational potential energy being equal to negative g m lowercase m over r. That is the universal gravitation constant. We see it here. The mass of one of the bodies, the central one, it's capital M and its unit is kilogram. And then the mass of the body that's orbiting the central body. That's the satellite. Earth is the big M, little m is the satellite. Or if we're talking about the Earth going around the sun, big M is the mass of the sun, little m is the mass of the Earth. Okay, big body, central one of the foci of the elliptical orbit is the capital M. Lowercase m is the mass of the other body, the one that's orbiting. Both are kilograms. The distance between the two bodies from the center of each of the two bodies is r. Distance of the center of the main body to the center of the orbiting body is r. This is the radius of it, right? This is how far we are from that foci to where we have the orbiting body in its orbit. All right, let's break this down with an actual problem. A shuttle with a mass of 103,000 kilograms is flying 370 kilometers above Earth's surface. How much potential energy does it have? We have to know some things about the Earth. First of all, it has a mass of 5.97 times 10 to the 24th kilograms. That's a lot of mass. The radius of the Earth, as we saw earlier, is 6.378 times 10 to the third kilometer. Okay, roughly 6,378 kilometers. Let's plug in the equation. When we plug these numbers in, this is what we get. Gravitational constant, 6.67 times 10 to the negative 11 meters cubed over kilogram of second squared. This is a known value. We think of it as being constant. For all intents and purposes, it is. We know the mass of Earth, 5.97 times 10 to the 24th kilogram, and the mass of the space shuttle. In this case, we're talking about the orbiter, but we get it, and it's 103,000 kilograms. We divide this by the radius. Now, here we have a few things. Radius of the Earth, because we need to go from the center of the Earth, so we need to know how big the Earth is, has a radius of around 6,378 kilometers. But we need that to be in meters. So we then turn this into 6.378 times 10 to the 6 meters plus 3.7 times 10 to the 5th meters. Remember, that is the 370 kilometers above the Earth's surface that the space shuttle's orbiter is. So we have to get this into meters so that it cancels out this meter here. Okay? Or at least so that it cancels out some of it. Let's keep going. This leaves us with some energy, 6.1, negative 6.1 times 10 to the 12 joules. All right, this is the potential energy of the orbiter as it goes around the Earth using these values that we know to have. Let's look at the kinetic energy. Kinetic energy's equation is 1/2 m times v squared. That's the mass times the velocity squared over 2. Satellite is traveling at 6 kilometers per second and has a mass of 5,000 kilograms. What amount of kinetic energy would it have? Well, again, we just plug and chug. It's not hard math. This means the kinetic energy here, K, is equal to half of 5,000 kilograms times 6 times 10 to the third meters per second squared. Now, we know that it's traveling at 6 kilometers per second, but we need to convert that into getting meters for this equation to work. And we know that we have 5,000 kilograms, so this gives us a result of 9 times 10 to the 10th joules. And you can do the math if you'd like. So I'd recommend you pause the video and try. All right, we quickly ran through how do you calculate those. You should know this from POE or from some physics class that you've taken in the past. If we combine the potential and kinetic energies, then we get the total energy of an orbit. So E is equal to my U and K. E is the negative GMM over R plus 1/2 mv squared. So it is equal to my potential energy plus my kinetic energy. Now the question might be, where did this come from then? And I'm hoping that you kind of see the overlap here, but let's break it down a little bit. Circular orbits, a force of gravity between a planet and the sun is F equals capital G, right, that gravitational constant, times the mass of the sun and the earth, the smaller one, divided by the radius squared. That is the force of it, not the energy, but the force of it, okay? Potential energy is force times an elevation. Gravity force is centripetal. So gravity force here is capital G, capital M, little m over r squared, and the centripetal force is mv squared over r. When we set those two equations equal to each other and then we solve for mv squared, we get gmm over r. We have E as being, or U plus K, our potential plus kinetic energy. And if we set those equations up right, we see that mv squared is also equal to g m over r from our connection between the gravity force and the centripetal force. All right, little bit of some fancy footwork here, and what we can find is that we result in negative g m over 2r. Again, it's not a math class. I want you to see the equations and how they break down and apply what you've already learned. So take a moment to look this over. And what I want you to understand is that the combined potential and kinetic energies, E, can be simplified all the way down to negative g mm over 2r. So what if we want to go from one orbit to another? How much energy do we need to do that? So we're talking about changing the altitude of orbits. A new station wants to move one of their weather satellites. It has a mass of 12,000 kilograms, and it needs to go from 650 kilometers above the Earth's surface to an orbit of 800 kilometers above the Earth's surface. How much energy do they need to get it from one orbit to the other? So, step at a time, let's go through it. I like to always make sure I know what the equation is that I'm using, so I would write it down. My total energy for this change in orbit is potential and kinetic being added together, knowing how much energy this satellite has because it wants to fall back to Earth and how much it has because it is moving. All right, potential, kinetic. And that is equal to negative GMM over 2R. I plug in my equation. My first energy, my first amount is for calculating 6.67 times 10 to the negative 11, right? That's my G. And then I have the mass, 5.97 times 10 to the 24 kilograms of the Earth. And then I have the mass of the satellite. And then I have the 2, that's the constant in this equation. And I know how big the Earth is. That's this 6.378 times 10 to the 6 meters, plus how far I am from the Earth's surface, 6.5 times 10 to the 5th meter. Plug this all in or do this math by hand. Either way, I'd use a calculator, and I wind up with negative 3.41 times 10 to the 11 joules. Again, you can pause the video and test the math out yourself if you'd like, but this gives me the first energy that I have. My first orbit's energy. Let's get the second orbit's energy. So what I need to get to, what I need to have to be in that other orbit. I do the same equation, I just change up some of the numbers. This one stays the same. This one stays the same because the Earth hasn't lost any mass. This one stays the same because satellite hasn't lost any mass. We are assuming that it hasn't lost mass, even though it might have to burn some of that to get into orbit. Again, introduction, not overcomplicating it though. We still divide by 2 times that radius, and the radius has changed, but not because the Earth has changed, because the distance has changed that I am from the Earth. So instead of being 6.5, I am now 8. All right, moving along, I get a negative 3.33 times 10 to the 11 joules here. The change in orbit then is my new orbit minus my old orbit, right? So how much I need to have as an overall change. And that is a simple subtraction of this math, and I find that it is a positive. This signifies the energy must be added to the system to change the orbit. I needed to add 8 times 10 to the 9 joules to be able to get this satellite to go from 6.5 to 8 kilometers away. Or 650 to 800 kilometers away. Alrighty, moving along. You learned in this some of the basic physical properties that are involved in transferring orbits. 1. Potential energy and kinetic energy are 2 main orbital energies. And 2, combining both to find the total energy of the orbit is important. And 3, with both orbit energies, you can then subtract them from each other to determine the energy to transfer between the orbits. Obviously, if I have to go to an orbit that's further out, I need to add energy to the system. And if I need to come into a closer orbit, I need to remove some energy from the system. I hope this makes sense. I know this is by far not nearly as complicated as the introduction to orbital mechanics, but understand that you have to have that background knowledge of what it is that an orbit must do before you can start talking about how you have to change it. This is obviously just an introduction to these things. It is way more complicated than just saying we add or subtract some energy, because we do in the end have to consider maintaining that eccentricity, maintaining an inclination, maintaining the shape, the size, the orientation, all of that, also while changing something about the orbit, and changing something about the mass of the satellite, because we have to burn fuel to get it to change that orbit. So this isn't something that we would do a lot. We would try to maintain an orbit most of the time, occasionally having to change its orbit, but we know its mission life, and we know whether or not we can service that satellite. If we can bring it more fuel, then we can potentially do that with some servicing launches. Otherwise, we have to know that it burns a certain amount of fuel, and we work that into the equation as well. Or we have to consider what its mission parameters are whenever we launch this satellite, and know that we might need to make some burns to get it into different orbits and give it enough fuel to make those changes occasionally. So again, much more complex than we might think, just with these simple equations. Hope you enjoyed it. Talk to you soon.